And in order to get to that, we need a load at the surface. It is, after all, a foundation being placed on the surface in this simple example. And that's load over area, 208 kips over an 8x8 foundation. And that's 3250. That is at the surface. So we use this value in the M&N chart as our loaded area at the surface. And we will evaluate delta sigma at the mid-height of the clay layer. I had some groups considering where should that be. It is most common to do it at the mid-height of a layer because that would be representative. And if you want to get more precise than this, more representative than this, you would subdivide it into different layers and then work at the mid-height of each of those sublayers. And in looking at the M&N chart, we need to consider 9.5 foot below the base of the foundation, which takes us down to that mid-height of the clay. And it's the Boussinesq chart, which I'm utilizing here, which gives you the stress distribution at the corner of a foundation. The problem is requesting under the center. So we need to come up with a little foundation over here and then multiply the effect of that by 4. So M is going to be 4 over Z, 9.5, and that's 0.42. And by the way, that equals N also. So B over Z and L over Z in this case are the same. I came up with an influence factor of 0.063. And the change in stress due to that loaded area is the Q value acting on that loaded area, which importantly is 3250. That's the whole amount. You don't squish it down to a smaller, the load isn't being carried by a smaller size. We're just compartmentalizing that into 4 pieces. And the summation of influence factors here would be 4 times that individual component. So 0.063 gives us the effect of that shaded region, and we have 4 such shaded regions. And I came up with 819 PSF for a delta sigma at that location. How are we doing on agreement there around the class? That reasonable? Did we have general agreement with 800-ish? Of course, it's your own judgment on what the number is on a chart and so on. It can be a little bit subjective, but we close? Good. Good to see. Cool. All righty. Thank you. We can go back to that solution and check out a starting stress, sigma naught prime. That would be total stress minus minus pore pressure, excuse me. And that's going to be 708 PSF. And a delta sigma is going to be 1520. The 819 gets added to that to bring us over to our final settlement at the end of this, which is 1527. And we know that the pre-consolidation stress, the knee of that curve is at 1,000. So we have a starting point of 700, a knee of 1,000, and 1,500 for the end point. That shows that we're in that case 3 that I had outlined in the consolidation lecture of needing both terms of the equation. We need both the C sub R, the shallow slope, C sub R or C sub S, depending what you call it, and the C sub C component. So both terms need to be in here. An important aspect here is that it's the entire clay layer thickness. We'll get to the, drainage, and if you take that in half for a double drained and so on, that comes in only to time rate stuff. But settlement itself is a strain-based calculation, and it's the entire clay layer, 9 feet thick, which is straining indeed. So we need to have that be the full amount. The rest falls into place quite readily with 1 plus initial void ratio, 1 plus initial void ratio down here. And in this equation, or in this fraction, I should say, it's always ending point over starting point. And you're just doing it for the first link of that and then for the second link. And this comes out to 4.6 inches. And given that we had pretty good agreement on the delta sigma, I'm going to go out on a limb here and expect that this will remain pretty consistent throughout the group as well. 4.6 inches. Are we getting agreement on that? Anyone? Good. Cool. Good stuff. Thank you. Next up, settlement after 2 months. And that's a question mark. So first up, we need to define C sub V. And CV is a soil property. And I had some groups rattling around with the concept of the hydraulic conductivity and the A sub V and so on. And we don't have enough information to piece it together that fundamentally, but we do have sufficient information from interpretation of data to be able to use this equation. And in time rate of consolidation, this is generally the go-to equation, meaning you will use this frontwards, backwards, sideways, inside out, and so on. And oftentimes you're solving for something different when you're in this equation. This time we need to solve for C sub V. And by the way, we need to solve for big T first, big T 90. And that means 90% of consolidation complete. I had provided some equations last time, one for degree of consolidation greater than 60. That would be the case here, since we're at 90. And one for less than 60. So you could utilize that equation for greater than 60, and you should come up with a number about like that. I just grabbed a number here and was able to write it down like it's a constant because this is an extremely common number to be using. So there's two numbers that would be known to people that do this quite regularly. One is T90 and one is T50. And in the next half hour, you'll see why that is, and I'll provide some shortcuts to where you can actually grab this number as effectively a constant for that specific case. But I was encouraging the groups to get into those equations so you get some experience with them and so on. And you should end up with somewhere right around 0.848. So with that information, you can solve for C sub V, a soil property, which is 0.848 times 1/2 inch. That's because it's a 1 inch specimen, double drain, top and bottom. So the maximum drainage distance there would be half the height, or 1/2 inch. That value squared over 135 minutes given in the problem. And this leads us to a number something like that. And it's common to have numbers where you get into 10 to the minus 5, 6, 7, and so on these, especially when you're in the meter squared per second kind of units, which are quite typical, by the way. And then we apply this. This is just a soil property. So this is like doing a stiffness test and then saying, how much is it going to pull in the field for a steel bar or something like that. Well, this is a soil property, and now we're going to grab that soil property and apply it to the field situation. We're using that exact same equation that we did earlier. We just rearranged it. It's the same one, though. And therefore, little t is going to be 60 days, 2 months, times 24 hours, times 60 minutes per hour. And It's double drained. Now we're in the field. It's very important that you recognize you're now dealing with field dimensions, so it's a much broader scale of dimension, and your numbers get very large accordingly. With timing for this process to occur, it's usually pretty quick in a lab setting, but in the field it can be a good long while. And that double drained allows for that to be the 9 feet divided by 2 is where this is coming from. And we have a t. This time this is unknown. We don't know what t is. And c sub v is here. With this, we rearrange and we solve for t being 0.046. Question mark here is how much average degree of consolidation is completed at 2 months. We have a t-value, but we don't know what that corresponds to. And we again go back to these equations where it's different for less than 60 or more. And I just go out on a limb and say, okay, a 9-foot thick layer, I'll assume it's less than 60%. That's quite a reasonable entry point to this. The t-value is pi over 4 times u squared. That means we can rearrange this to be u is the square root of 4 time factor over pi. And what we end up with is 0.242 or 24% of consolidation being complete. By the way, this does check with the assumption that it was less than 60, so that tells us, hey, we use the right equation. If you end up outside the range you assumed, that tells you you use the wrong equation. And the amount of settlement at 24%, this should be a 4, not an 8, is 0. Or the amount of settlement at 2 months, let's say, which is 24%, would be 0.24 times the total amount. That 4.6 is what's going to happen at time infinity. And this is saying the u being 24% is saying you're 24% of the way done with consolidation process. So therefore, the settlement at some time t at 2 months is u average times s ultimate. That's where this is coming from. And this indicates that 1.1 inch has occurred after a 2-month period. Are there questions on this? Let's say that we had agreement with the value here first, but 1.1 inch-ish, is that working out? We good? Cool. Good stuff. I'm seeing a few thumbs up here and nods, so that's good to see. So that covers time rate of consolidation. And I realize we had quite, I'll call it deliberate coverage of the topic in the course with, nearly an hour and a half devoted to breakout groups on that. But I really like that because it gets you into the equations and thinking on a cold take of just never having been through a problem of this sort of thing. Really, how do you get through this? And starting to piece the theory together and so on. So I do hope that was worthwhile for you. And have a bit of other content here related to time rate of consolidation. And hold on here. I have a consolidation handouts, consolidation settlement handouts I'd like to run through. That is a packet, 8-page packet that has been presented on Canvas site for you, so you may follow along or just know that this exists there for your reference. And I'd like to zip through this, and it will provide some guidance most certainly on homework 5 that is in process, I understand. So first up is the stress-time relationships. And we have total stress, in which you just have a step load occurring. And that would be at time of construction, assuming it's instantaneous. There are situations where you can have that kind of thing, of a very quick loading of a site and so on. Moving a building or something like that. But typically that takes a bit of time, so it would have some slope to it. But in any event, it is a step of some sort. Pore pressure is going to similarly jump upward. Effective stress would be the difference, and slowly that stress would be transferred over this means to the soil skeleton and take a long, long time to do so. Most of the transfer occurs at the onset, and then it slows. It's kind of an exponential process. The void ratio, meaning the settlement here, and those two are certainly connected. The void ratio would go down at time of loading and would continue to change, but at a lessening rate as time continues. And settlement similarly would start out at quite a high rate and then level off to not much happening out here, but a little bit of settlement still occurring real late in time. And we're speaking here, years and decades out kind of timelines. This is a graphic associated with the determination of the pre-consolidation stress. And this is requested of you in homework 5. There's a second problem there that is some lab data for you to analyze. And one component of that is the stress aspect. And the Casagrande procedure was developed. He's the fellow that came up with the liquid limit device, by the way. So a heavy hitter in geotech, by the way, a real founding professional. And let me get this down in size a bit so we get it all on the same page here. And this is your consolidation curve. Okay, so up until now, we've just been calling it a knee of the curve and saying, hey, it's right there at the obvious knee, but there's some refinement to how you can get to an actual value for that when you're dealing with real data and you have some curvilinearity to this shape. And the first is choose by observation the point of minimum radius or maximum curvature. So effectively, eyeball the knee of the curve, in other words, and find out where that is. That's point A. And then you draw a horizontal line from that location. At this location, you will draw a line tangent to the curve at that same point. And that's right here. That's this curve right here. That is tangent to point A. So now you have a horizontal line and a tangent line intersecting at point A, and then you will bisect the angle made by those two lines, and that brings you into this middle line here. So now you're able to construct that line, and then finally you extend a straight line portion of the virgin compression curve, meaning this portion down here, the normally consolidated portion, sometimes called the virgin compression curve. You extend that backwards straight as a tangent to that portion of the curve, And where it intersects this bisector is your best estimate for preconsolidation stress. On this graphic shown as sigma prime P. Questions on that one? It's a reasonably straightforward graphical process. It is, spelled out here pretty cleanly. You're being expected to do this for one set of data, and I included in this class because on the quarter system, you don't get to see this at the 382 level, where many universities around the nation on semester schedule would do consolidation tests as part of their normal semester. And we cut the curriculum a little bit thin for the lab portion of geotech here. And I think there's some value in having some experience working with this kind of data and making these judgments and so on. So, any questions? All righty. Next up, there is another of our friends, Schmertman. You guys recognize that name from immediate settlement over sands and all the work he did. He also did some work on consolidation. And it related to correcting a consolidation curve. You'll see this arrow here is the actual curve, and that would be from a laboratory specimen. And what Schmertman was claiming is that a lab curve is typically going to be dampened a bit, and you'll actually end up with a lower slope than you would in a virgin in situ condition, meaning in place, actually in place. And he goes through a methodology here in which you identify an E naught. And I don't have all the steps laid out here. I'm not expecting you to do this one. I just want you to be aware that this kind of process does exist. And that if you have lab data, you have to recognize that, hey, that has been disturbed some by being pulled out of the ground, put in a tube, taken out of the tube, put into a specimen holder, carved out to the right shape, and then loaded up. And all of that disturbance tends to make this a more curvy kind of response than you would get in the field, where it's going to be a cleaner response of a sharp edge for reconsolidation stress, and therefore a steeper C sub C value, a higher value for C sub C than what you would measure in the laboratory. So I just want you to be aware that, there is some work to document that field value should be a little bit higher than a laboratory measured value. And I don't expect you to do a whole lot with that in this class quantitatively. Just be aware of it. I think this is the kind of packet that can serve you well as you go out for the industry or future endeavors and so on. It can just be part of your knowledge base, and you can look into this method, the Schmertman technique, if you have a need to. There are some empirical equations for C sub C and C sub C epsilon. And C sub C is the value of compression in relation to a stress void ratio relationship. And this brings up a distinction between those two frameworks. And I don't believe this was included in the video on consolidation, so I will share it with you here just so that you've seen this in the event that it was not in that video. And this brings in the conventional consolidation plot on top, a void ratio versus log of effective stress. And we have a knee of a curve, that'd be pre-consolidation stress. The shallow slope above it would be C sub R. The steep slope in the virgin portion of the curve would be C sub C. And what is shown below is a very similar looking curve. It is instead strain versus log of sigma prime. And you'll note that the shape of the curve is identical. It's more or less just a scaled diagram of this plot. And every data point simply has been converted from a void ratio basis to a strain basis. And C sub R epsilon is calculated very easily as C sub R over 1 plus initial void ratio. And C sub C epsilon is C sub C over 1 plus initial void ratio. And if you utilize these strain-based properties, it simplifies your consolidation settlement equations. I'm sorry, this thing's going crazy here on me. And the whole over 1 plus E naught disappears from those equations, so it has a easier looking appearance, I'll say, in terms of those large equations that have two terms and the log of the fractions and so on. It really means the same thing, but sometimes there is a desire to be working on a strain basis for these compression properties instead of on a void ratio basis. And there's folks in both camps. The strain is quite easy to keep track of and easy to apply then for settlement. So there's certainly some guidance to be using those parameters. However, the void ratio gives you a real sense for what type of soil you have. And if a soil is going to start at an oddball void ratio, like a 2.8 or something, you know, an organic silt or something, or heading into a peat, which might have, you know, void ratios of 6 or, you know, 8 for a starting void ratio. Knowing that number at the onset does help and provide some context for the problem. So in that regard, there's some value for using the void ratio version. So both are used quite a bit. I can't say there's a, you know, preference on one over the other so much, but it does allow for a comparison between these two. And I'll go back to that handout now. Which had some equations for C sub C and C sub C epsilon. And I would call these some kind of worst case scenario, meaning don't go to these. If you have data, and for that matter, in the projects that you have, for instance, homework 5, you have data. So don't come here for your values. Actually, you can solve for it and be doing much, much better. These are just empirical correlations to some of these parameters. And you're trying to say that, hey, I know my liquid limit, so therefore I can estimate my C sub C. And simply basing a CC on a liquid limit, you're not going to be getting a real high quality value. And these are typically only relevant for certain soils. And mind you, you can apply them outside of those soils if you know you have similar conditions, but also there is the condition where they are limited somewhat for, inorganic, or down here we have some for organic and so on in that regard. But you see that they are related to plasticity characteristics, void ratio characteristics, water content, and so on for these. There are some typical values for C sub C, just to give you a feel, an intuitive feel as to, hey, what should these numbers be around? And, they're ranging from 0.1 on up to, 15 shown in this table. So it's quite a large range. And it's the high ones are coming in for Mexico City clay, and specifically peat is extremely high as well. So both being highly problematic from a settlement standpoint. There are some ratios of C alpha to CC. We haven't yet talked about C alpha. I intend to yet today. And here is the graphic. I think I had shown this in a slide last time of T versus U average. So this allows you to actually get a number directly. So if you have 90%, you could come in at 90% here on this line, shoot to here, and come up. And where are you going to be? Well, you should be right around that 0.848 is what I was suggesting earlier. You could use the equations to get there as well, and that either would be fine. The equation is probably a little bit better than just a graphic and eyeball sort of thing. You'll be able to be a little more precise down here, but it's again geotech, so there's not a need to get out to 6 decimal places anyway. This is a graphic of the collapsing excess pore pressure with time. So as a layer of compressible soil is loaded, it would gain pore pressure and actually hold that entire load, and then, as is shown here, would dissipate towards the drainage layer shown on both top and bottom. And we had been through this graphic last time, but this allows you to see a connection point now between T values and average consolidation ratios. And you'll see that for that 0.848, which is actually identified here for the 90%, it is highlighted here. You're going to end up with the peak of that parabola being less than 90, and the edges of it, of course, being greater than 90. They're right at 100 just because they're draining instantaneously, immediately. And it's, if we represent that parabola as an equivalent rectangle, that's where we come up with the 0.9 on this. Now, I'd like to show you 2 methods that can be used for laboratory data, and you'll be using these in homework number 5. And these are both methods to arrive at C sub V. And what do you know? You're going to use this same equation again that I said you'll be using a whole bunch. So we'll get to that in just a minute. The first is called the logarithm of time method, sometimes called the T50 method because it applies to determining the T50, as you'll see. And what you do in this case is plot your consolidation data on a log scale. And this dark curve would be the general shape that you would expect a consolidation increment to look like if you plot it on a log scale. This would be a 24-hour increment, would look something like this when plotted on a log scale. And what you're going to do It again gives you step by step. So it's real cleanly described here, and you have access to this. So I figure just a quick pass through this today will be sufficient to get you up to speed with it. The idea here is extend straight line portions of primary consolidation, and this straight portion down here, by the way, past this lower knee of the curve, is actually called secondary. We'll be seeing that just a little bit later today. Extend straight lines to identify that knee, which is point A. And we shoot that A point over to the y-axis and call that D100, the deformation at the end of 100% primary consolidation. This point down here is sometimes called EOP, end of primary, meaning that's the end of primary consolidation. After this point, it's only secondary compression that is occurring. The initial curve portion of the plot is approximated by a parabola. And what you're going to do is select times T1 and T2 such that T2 is 4 times T1. So you just jump in here and grab 2 arbitrary points, one there, B, and one there, C, making sure that point C is occurring 4 times later in time. So you might take a 1-minute reading and a 4-minute reading, or a 2-minute reading and an 8-minute reading. It should be near the beginning of your consolidation curve. So somewhere up in here, you should be doing that. And what you'll do with this is identify that distance X between those 2 points. And what you do is you flip that over, moving upward. So you'd start like this. I'll put on a dark background, my fingers, and cross it back up. So you have X identified here, and you simply flip that X upward to be the same value X going above point B. So you first determine what is the vertical distance between B and C, and then you say, I'm going to project that upward from point B, and that gives you a point D here. And we make a horizontal line at that point and call that D0. That's initial condition. The D0 would be deformation at 0% consolidation. We can identify from that the average of those 2 points, numerical average, which will be D50. We have 0 and 100 identified. 50 will be right between them, the midpoint between them. So we find 50, and we shoot over to the curve at that point, and where it intersects, being point F, will give us little t50. And recognize that you're reading this off of a log scale, so you have to be careful that you're interpolating properly on a log scale. At that stage, you can go back to this equation, and large time factor for T50 is kind of like T90. It's a known number. It's 0.197. You can also go right back to those equations if you want and solve for it, but there's not really a need because these are completely standardized numbers that are used. So big T50 is 0.197 by definition, big T50. C sub V is what we're solving for. Little t50 is what we just found on the graphic. That's this point here. And H drainage squared has to do with whether this is single or double drained. And remember that you're dealing with a small laboratory specimen. So it's on the order of, 1 inch or 3/4 inch or half of that. And that lets you rearrange this to solve for C sub V. That's how you would get it for the T50 method. There's a separate technique which is quite similar, which is called the square root of time method or the T90 method. In this case, you'll make a new column in Excel and take the square root of time. You have a time column, you'll simply take the square root of that. So you'll plot your consolidation data for that one load increment, and you'll do that versus square root of time. And it'll have an appearance something like this. First up, you draw line AB through the early portion of the curve. That's pretty loose guidance, but you see what is done here. AB, you're finding, a tangent to this main early portion of the curve is what you're doing, and having that come down to point B. And then you'll draw line AC to ensure that the distance between origin and C is 1.15 times that of origin to B. So you get this distance and then multiply by 1.15, that gives you point C, and you shoot back to point A. It's another graphical type technique, and you will intersect your curve right there. And in this case, you will identify T90. You'll actually identify square root of T90, since this is a square root of time axis. And you take that number, you square it, and that gives you T90. With that little T90 known, this time you know that one. You're solving for C sub V. H drainage squared is, again, your specimen height, either single or double drained, either the whole height or half the height, depending on that feature of single or double drained. And this time, big T90 is 0.848. So this is, again, a standing value that you can just use whenever you're evaluating T90. You can just grab that number specifically, rearrange it, and solve for C sub V. So you have some consolidation data provided to you in homework 5 as part of the second problem. One of the parts of the data is an increment of stress change, just one time series of deformation versus time. And you will plot it using the square root of time to solve for C sub V using this T90 method. You'll separately plot it using square root of time axis and determine T50 and get it a C sub V using the T50 method. This gives you some typical values for coefficient of consolidation. Again, I provide these just simply so you have something in hand to say, hey, what are some numbers? Is this reasonable kind of thing? And you do see that it's quite a range provided here. And we have a plot here presented by the U.S. Navy. This is out of that NAVFAC manual, by the way, that I have commended on occasion in this class. This gives you a C sub V value for relationship with liquid limit and working with remolded samples versus undisturbed samples. So you do have a difference in the behavior. And CV is provided here in meters squared per year or centimeters squared per second. Double y-axis in this case. Questions on this?
The homework also asks us to find C sub alpha, but the only thing the textbook says about that is it relates it to the soil properties, but we don't know what kind of soil we're analyzing.
Okay, and I'm about to share with you some graphics that get on that exactly. And that is the topic of secondary compression. So let me change the screen share here. And identify that secondary compression occurs due to long-term rearrangement of the soil skeleton under a constant effective stress. And it's commonly assumed to occur after end of primary consolidation. So in the last graphic, that log time method, we actually found that end of primary near the curve, and the secondary settlement is assumed to occur after that. It's actually been proven to be happening during consolidation also, but I don't want to muddy the water getting into an academic argument and try to push a complicated theory in that regard. We'll just use that it is, in fact, occurring after end of primary. Would be fine for this class. It is prominent, meaning secondary compression is prominent, and particularly problematic in organic soils. And the calculation of that will look like this. So secondary compression is the long-term settlement. It's creep of soil. That's the mechanical entity that's occurring, the mechanism that's occurring in the soil is creep. And, it looks like this on a graphic. You can plot void ratio versus log of time. So this is very similar to the graph you saw with the T50 method, which was that exactly. And C sub alpha is simply the slope of this line down here after the knee of the curve, which is called end of primary. And that slope is defined on a semi-log plot like this as the change in void ratio for one given log cycle of change in time. So the rise for a given log cycle of run, in other words. And that's the same as C sub C and C sub R. They're all the same methodology to get to them. And for that matter, these can also be defined on a strain basis as well. I have it shown here as a void ratio, but there would be a C sub alpha sub epsilon where this axis would be epsilon. And the conversion between those two would again be C alpha over 1 plus E is going to give you the C sub alpha sub epsilon. So this is a means of getting that value. So you'll be utilizing that to arrive at that. And if you need to calculate secondary settlement, which I think is needed in one problem, you do it this way. And this is the last slide. The amount of settlement for secondary is that C alpha times H, complete layer thickness, over 1 plus starting void ratio. In this case, recognize that that's the end of primary void ratio, times the log of T2 over T1. And that's going to be an end time over a start time. Typically, that start time would be end of primary. So the look and feel of this equation is very, very close to what you have for consolidation. That's a stress-based calculation. This is a time-based calculation, but the framework for the analysis, that it's a semi-log plot and so on, remains the same. And I'm sorry for running over here by a minute and a half. So, sorry. No class on Wednesday, as mentioned. So, see you early next week. I expect homework 5 to be due Tuesday-ish, maybe Wednesday of next week. So just as a heads up on that. So it'd be good to get into that in earnest in the next coming week. Good luck and have a good weekend, or a good week, I should say.
Thank you.
You bet.